introduction to Mechatronics as code. I'm Seth. You can find me on GitHub. You can find the projects I talk about on GitHub. And there's also a link in the conference program to the project I'm talking about. I'm a software developer, but I have a background in electronics. And I contribute to open source projects where I can. I'm also a Code Club volunteer here in Wellington. So in this talk, I'm going to explain what is Mechatronics, why should we use code, and then I'm going to introduce CadQuery, which is a Python library for mechanical design. And then I'm going to introduce Atopile, which is a language used for defining electronic circuits for designing circuit boards. And then I'll just show a few highlights from an example project I've been working on using these technologies. So Mechatronics, what is it? It's a bit of a buzzword. But it makes for a catchy title. It's a branch of engineering, this is from Wikipedia, that combines mechanical, electrical, electronic, and software engineering. So examples are all around us. Cars are full of sensors, actuators, and software. Not just robo-taxis, but all cars on the road, almost all. And within a car, there's subsystems which can be considered mechatronics, such as ABS, braking systems. Factory automation's a big one. Spacecraft and planetary rovers. It was actually the Mars Curiosity rover that got me into this, so I'll explain that later. And hobby robotics. Oops. Oops, oh, sorry. So, why use code? Well, because we're developers. Code is text, meaning we can use the tools of our trade. We don't have to leave our favorite text editor. And code means reliable diffs, meaning we get all the familiar advantages of version control. We can write unit tests, and we can run those tests in CI pipelines. Another reason to use programmatic design is we can have manufacturing files as an output of our programs or applications. In this example, we have a app which will design an enclosure for us. We can put in a width, a length, and a height, and then the program will create a box for us with those dimensions. This is an example of parametric design, which means a program is not limited to creating an enclosure of a single size. Another reason is convenient reuse. You can reuse your own or others' designs. Components or parts can be published as packages or some sort of installable module. In this example, a package has been installed from PyPy, and we're using it to instantiate a 5mm washer. So we don't need to create our own. Okay, mechanical design. This section is mostly going to be about CadQuery, which is a Python package for building parametric 3D CAD models. Because it is Python, it can be used in applications alongside other Python packages, meaning our designs can be backed by the entire Python ecosystem. Now, CadQuery is built on top of the Open Cascade CAD kernel, which is written in C. And that CAD kernel is used in a lot of CAD applications, including FreeCAD. Now here's a real product on the market designed with CadQuery. It's by FX Bricks, who sell Lego-compatible train tracks. FX Bricks have documented their CAD pipeline notes, which is worth a read. You can find their repo on GitHub. Now, so the design is not public, just the way they make it. It's a commercial product. FX Bricks specify each of their products as configuration, and then it's passed to a model generator written in CadQuery, and it outputs manufacturing files, 3D printed prototypes, but they also went professional and used injection molding. Okay, so we're doing mechanical design in code, but visualization is a very important part of CAD. You need to see the physical object that you're going to build. So this is a screenshot of CadQuery. It's more like an IDE. It's written in Python using the PyQt framework. Now there's the editor pane here with the CadQuery code. This code runs and outputs this robot frame, which is actually the beginnings of a model Mars rover. Now, I prefer not to use the editor within CadQuery editor. I use PyCharm, so I close the editor and work in PyCharm and just do the visualization here in CadQuery editor. It's got some useful debug panes and a console. Now, here's a simple plate defined with CadQuery. This is, well, it can be considered the hello world of programmatic CAD. Here, we're defining the dimensions of the plate. And this, here, starting on line 7, we create a work plane. Now, a work plane is somewhere to start. It's like a virtual piece of paper that you can create your model on. And on that work plane, we create a box with our height, width, and thickness. And you can see that's how it's rendered in CadQuery editor. This is the previous example, but with a hole bored in the center of the plate. After the box is created on line 10, we select the face of the plate in the furthest in the Z direction. So we're actually selecting the top surface of our plate. That's what greater than Z means. We're creating another work plane on that face, and then we're boring our hole with our diameter of 22.
Can we keep questions to the end of the presentation, please?
So not everything has to be square, as the last two examples. Here's a cycloidal gear, which is generated with a function, which I've removed the content because it's quite long. But what we're doing is creating a parametric curve with the output of the gear function. And then we're twist extruding it to give it some depth. Okay, unit tests. We've got some basic designs, but how do we do unit tests? Well, a solid has a surface area which we can measure. A solid is made up of faces, which we can count. A face is constructed from wires, which we can measure and count. And we can calculate volume. So all these properties can be used in our unit tests. In the example shown, I'm testing that an assembly of parts has the expected dimensions. That is, it fits within a particular bounding box with an X length of 285. So that's the end of introduction to CadQuery. But before I finish off, I'd like to introduce build 123D. It's also a Python CAD package, and like CadQuery, it's built on the Open Cascade CAD kernel. So if you're evaluating programmatic CAD packages, it's definitely worth a look. Looks a little bit different. It doesn't use the fluid API as CadQuery. So here's the same example that you saw on earlier slides to build a plate. We're using a build part builder to construct a box. Okay, printed circuit board design. I've been doing printed circuit board design with Atopile. Now, Atopile can be pip installed. Now, in contrast to CadQuery, which is a Python library, Atopile is a compiler. So Atto is a domain-specific language for electronic circuit design, for defining electronic circuits as code. So it's written in Python, but the language you write is Atto. Here's a real product designed with Atto. It's a spin servo drive for use in robotics. This project is open source and the code is on GitHub, so it's a great example to refer to when learning Atopile. Now first up, I will just give an overview of PCB design workflow. First of all, you create a schematic in a GUI schematic editor. Then from that schematic, a netlist file is generated. The netlist file is imported into a PCB editor. You lay out your PCB and then you generate some Gerber files which can be sent to JLC PCB or somewhere for manufacture. Now, Atopile replaces the schematic in the traditional workflow. So rather than dragging and dropping components, the circuit is defined in Atto code. And then the role of the Atto compiler is to convert your Atto code to a netlist. And then the rest of the process is the same traditional process. So here's an example, cut down example of some Atto code. In this example, we are creating a resistor with a value of 1 kilo ohm and a tolerance of 5%. In Atto, just like all real components, values must have a tolerance. That's enforced in the language. Now, once we've written our code, defining our circuit, this is not a real circuit, it's just one component. We build our Atto project. Okay, once we've okay, sorry. Once we've built our project, it generates a netlist, and we import the netlist into KiCad PCB design. And what Atto has done here is it's selected a footprint. This is a footprint of our component, and it's placed it in the PCB editor. And from here, we can do our standard board layout. Okay, so typically we'd want to make a more complex project. Just a resistor is not much use, so we're going to add a LED to make it a LED indicator. So we define our LED. Now, LED has two important properties, a forward voltage and a maximum current. So we're defining those here. And a LED has two pins to wire it up, an anode and a cathode, pin 1 and pin 2. And then we use the tilde operator to wire the cathode, LED cathode, to the one of the resistor pins. Now, if we import that design into PCB editor, we can see the resistor and the LED, and it's got a net line there, this green line. Now, that means we have to put a copper track between those two pads. This is a slightly improved LED indicator. We're using a LED from the Atto standard library. And what we're doing here is, on line 8, is defining the current we want that LED to run at. And the current corresponds to the brightness of an LED. So on line 12, we have a power connector. Then we create a LED indicator on line 15. And interesting thing here is, because we have our voltage defined on our power interface, 4.9 to 5 volts, and because we've defined the current we want the LED to run at, Atopile can automatically select the value of the resistor according to those parameters. And that's a complete circuit imported into KiCad PCB editor. power connector, LED, and resistor. Another great aspect of Atopile is it supports packages. So packages contain reusable Atto code in the form of modules and component definitions. They contain footprints, and they can contain snippets of PCB layouts that can be reused. Here's a screenshot of the Atopile package registry. You can see at the top there's a USB connector there, which is a pretty common component these days. So that's a brief introduction to Atopile. The workflow depends on KiCad, which is an open source PCB editor. And not the whole, just the initial process is code driven. The PCB layout has to be done in the GUI. There's two other projects which are worth considering. Skiddle, that's been around quite a few years, still quite active. And Fabric as well. They're both software-defined EDA tools, as is Atopile. But the difference is that both of these tools are Python libraries, and you define your circuit in Python rather than another language, custom language. Okay, on to the example project that I am using to learn these technologies. I discovered programmatic CAD and programmatic electronics design soon after I started these projects. This project, and the project is to build a quarter-scale Mars rover. And I'd like to highlight a few of the ways I have structured this project. So my whole project is a Python package. There are sub-packages for the electronic design, the mechanical design, and a sub-package for a custom Sphinx extension to build the documentation. This warehouse sub-package contains reusable mechanical components. The whole project is managed with an executable script. The build sub-command will create files for manufacturing files, for example, 3D printing. That's just a helper function I wrote to reduce bloated DXF files. This export PNG creates a PNG image, raster image of the rover from the code, which is also used in the Open Graph card. There's a sub-command for generating a bill of materials, and I have a sub-command here which generates the PCB outline for one of the PCBs. So that same command generates a manufacturing files archive containing the bill of materials files for 3D printing and some CAD files. Now, I spent quite a lot of time structuring my project at the beginning because it's more than just a single script. I developed my own abstract base classes to wrap the CadQuery code. So this wrapper contains wraps. This abstract base class wraps a work plane object. This one wraps an assembly, and it's got helper functions for generating the bill of materials. And documentation. Documentation's a big part of this. I want other people to build it, even though I haven't built it myself. So I'm using Sphinx, and I've got a Sphinx extension which will generate 3D models from the Python code and embed it in this Sphinx documentation at build time. So if you go to this, the documentation page, you'll see that this model can be rolled, panned, zoomed. The bill of materials is generated at build time. So it's always up to date. These components are extracted from the Python code. Thank you very much.
Okay, so we have time for 1 or 2 questions. Who wants the cube of questioning? All right, Yeet. Can we have the cube of questioning switched on? There we go.
Couple of questions for you. First of all, with the CadQuery piece, knowing that it's got an open cascade background in it, it produces NURBS B-reps as the topology for the parts. If I wanted to make a mesh for doing CFD or FEA analysis with those components, do I need to utilize a different library or different piece of software for doing that, or can I do that within CadQuery itself?
You'd use a different software. There's actually a CadQuery extension, mesh extension,
okay,
that you could use. I haven't used it myself.
All right, no worries.
But yeah.
Anyways, my second question was in relation to Atopile. So in one of your slides, you showed code for producing a resistor and LED and that sort of thing, and you mentioned that you can declare tolerances and things like that. One of the things that I noticed was missing was any definitions for the type of component. So
I'm going to ask that we move from statements to questions, and real quick if we can. Otherwise, pass the box on to the next person.
Yep, no worries. How would you in that code define whether it's a through hole or surface mount component?
So by default, everything is surface mount. But you can choose a specific part number from a catalog and put that into the Atopile code and specify a specific part, which would be a through hole part.
All right.
Yeah.
All right, next question. We have one over here, and that'll probably be our last question. Sorry.
Hello, thanks very much. That was such a cool model. I checked it out last night. My question, though, is how would you say CadQuery compares to OpenSCAD?
So I haven't used OpenSCAD. Okay. When I was looking for a library to use, I came across OpenSCAD. I didn't use it because it wasn't Python.
Very fair.
That's all I can say.
Fair enough.